Okay, today we're going to be talking about something called LHospitals Rule. So in your book, it's spelled out L-O. It's got this weird little accent thing over the O. This is a French name. That's why it's spelled all weird. One thing I just wanted to point out to you guys is that in a lot of other books, you're going to see it spelled Hospital. Like every university level textbook I've ever used spells L'Hôpital with the S. This is not pronounced LHospitals. Okay, this is your way to look smart in your first semester of calculus in college or second semester. That S is not pronounced. So, before we get into L'Hôpitals Rule, let's just kind of give you a little background about it. So, L'Hôpitals Rule is going to deal with limits. It's the last limit method that we are going to learn this year. Let's talk about the guy named L'Hôpital. So, L'Hôpital was a French mathematician. He lived from 1661 to 1704. So he was a pretty young dude when he died, but he was in right at the end of the 1600s. Now, we haven't talked very much about this, but the history of calculus itself is super cool. So calculus was essentially invented and formalized by, it's kind of an argument, was it Isaac Newton or was it Wilhelm Leibniz? And these two mathematicians, Newton and Leibniz, they kind of just had this decade-long argument about who invented calculus. And that big argument really came to a head in 1711. So L'Hôpital by this point was long gone. So L'Hôpital kind of created this rule, this theorem that we're going to talk about today, kind of in the middle of this argument that Newton and Leibniz were having about who invented calculus. Fun fact, that argument was never resolved. We haven't declared the winner of the calculus argument, but we do use most of Leibniz's notation. Let me put him up. So, history of math, one of the most fascinating things I've ever gotten to learn. So, let's talk about what L'Hôpital got us then. So what L'Hôpital did for us is he gave us a way to evaluate limits such as this one. Let's see. Such as the limit of the sine of x over x. So remember the first way that we always try to evaluate limits is that we just plug in zero. In this case, we get 0 over 0. And you guys did some practice last time knowing that this is called indeterminate form. So let's go ahead and talk about what indeterminate form means. Let me give you guys a couple examples. Let's say I wanted to take the limit as x approaches infinity of the sine of x over 7x plus 2. If I were to do direct substitution here, I would get 0 over 2. Whenever there's a 0 on top, I'm going to get 0, right? So this first limit, super easy to evaluate with direct substitution. Let's look at another one. Let's say I take the limit as x approaches 0 of 5 over x. I'm going to do direct substitution. I basically get 5 over 0. If the bottom is getting infinitely small, it means the whole fraction is getting infinitely big. So that limit goes to infinity. So this is what I mean by indeterminate. Notice that whenever the 0 is on top of the fraction, the limit goes to 0. So up here, when I plug in 0 and get 0 on the top, it feels like my limit should be 0. However, we also know that when the 0 is on the bottom of the fraction, the limit should be equal to infinity. So when I evaluate my limit of sine of x over x, it feels like, well, my limit should be infinity because there's a 0 on the bottom. So it's indeterminate. It's impossible to tell just from direct substitution, should that limit be 0? Should it be infinity? Should it be something in between them? So what L'Hôpital did is he gave us a way to evaluate these limits that are in indeterminate form. And the way we do that is we're going to look at their derivatives. So first of all, here, this blue graph is the graph of the sine of x over x. So one thing that we've done is we can evaluate these limits just by looking at the graphs of them. I'm actually going to separate this out. So I'm going to graph the sine of x, and I'm going to graph just the function x. Now, we're taking the limit as x approaches 0, so we're really just going to be thinking about this graph at the 0 mark. What I want you guys to notice is that we are dividing basically the green function over the purple function. And we want to look at how they're changing, because we know that a fraction, we're going to be dividing the top and the bottom. So we can just figure out, what's going on with both of those. We can figure out what the fraction will be. And as you zoom in and get closer and closer to 0, both of these functions have what's called local linearity. So at least on this interval, like almost from negative 0.5 to 0.5, both of these functions look like to be straight lines, right? And they both have the exact same slope. They're both changing at the exact same rate. So if we were to divide those two functions, we would get the exact same. We would just get 1, right? The same numerator, same denominator, so we get 1. And that is the idea that L'Hopital's rule is built on. It tells you, let me switch back to black. If we have the limit as x approaches any number of f of x over g of x, so two separate functions, if this is indeterminate, then we can take the limit as x approaches a, and we just take the derivative of the top function and divide it by the derivative of the bottom function. Okay, so we're just taking derivative of the top, derivative of the bottom. We're still taking the same limit. Now we're just going to differentiate. Okay, this is L'Hopital's rule. Put a box around it, put a star around it. This is one of my favorite ways to take a limit because it's just so simple. So let me go ahead and go through some examples, and I'll walk you through especially some of the important notation that you want to be aware of as you use L'Hopital's rule. Let's say you want to take the limit as x approaches 0 of the square root of 1 plus x minus 1 over x. Let me make sure you guys know that square root ends right there. So first thing you're always going to try is direct substitution. So notice that when I plug this in, I get 0 over 0. The first thing you want to do when you start thinking, hey, I want to use L'Hopital's rule, you need to show that you have an indeterminate form. So 0 over 0, that's indeterminate. So you need to show, hey, I took a limit, I got indeterminate form. Now I'm going to use L'Hopital's rule. So to use L'Hopital's rule, first you need to indicate that you're going to use it. I usually just put an LH for L'Hopital, but you could also spell out the whole thing. This limit, original one, is equal to the limit as x approaches 0. And then I need to take the derivative of the top. So I'm going to do the chain rule. 1/2 times 1 plus x to the negative 1/2. Multiply by the derivative of the inside, which is 1. Remember that negative 1, that derivative will just be 0. And then take the derivative of the bottom. One thing to recognize here, this is the only time that you will take the derivative of the top of the function and the derivative of the bottom function and not do the quotient rule. So we are not taking the derivative of the entire function of the fraction. We are taking the derivative of the top and then separately the derivative of the bottom. Okay, I'm going to go ahead and simplify this. This just turns into 1 over 2 square roots of 1 plus x. Now I can do direct substitution. I just think L'Hopital's rule is so cool. This is when you can do direct substitution. You plug in 0 now, and you get 1 over 2 times the square root of 1, which is just 1 over 2. So we get a finite number for our limit here. Okay, let's do another one. Let's actually look at a one-sided limit. Say I want to take the limit as x approaches 0 from the positive side of the sine of x over x squared. Okay, notice this is going to be 0 over 0, which is indeterminate. So that's my first thing. I've got to make sure I show the indeterminate form. I write that I've recognized it, and then I give some indication that I'm using L'Hopital's rule. So for L'Hopital's rule, I'm going to basically have the same limit, but now I'm going to take the derivative, so the cosine of x over 2x. Now when I plug in 0, I'm going to get 1 over 0. So that means I'm going to be having, my function's going to be going to infinity. But I want to, or negative infinity. I need to make sure I figure out, is it going to positive infinity or negative infinity? So I'm approaching 0 from the positive side, so I'm thinking about numbers that are just bigger than 0. So like the cosine of 0.1, cosine of 0.01, cosine of 0.0001. That's going to be a positive. It's going to be coming at the cosine from the positive side. Now 2x, as I approach 0 from the positive side, it's also going to be positive, which means this is going to be a positive infinity. Okay, let's do, I know the one-sided limit's going to be kind of tricky, so let's do the same limit, but let's come at it from the negative side and see how that might change my function, my limit. So I'm doing the same limit, but now I'm approaching 0 from the negative side. When I do it first or initially plug in, I still get 0 over 0, which is indeterminate. Okay, so I'm going to do L'Hopital's rule. I'm going to take the limit as x approaches 0 from the negative side of the cosine of x over 2x. Okay. So now I'm thinking about plugging in numbers that are just smaller than 0. So as I approach cosine of x from the negative side, the numerator, that's still going to be a positive one. The cosine is still positive from either side. However, as I plug in values that are close to 0 on the bottom, I'm going to get numbers that are close to 0, but they're slightly negative. So I'm going to put a 0 down here, but it's kind of like a negative 0. Okay, I'm thinking about that those values are approaching 0, but from the negative side. So if I'm taking 1 and dividing it by a really, really small negative number, that's going to be a negative infinity. Okay. So when you're thinking about these one-sided limits, you need to be especially careful about what are the signs of the top and the bottom of my fractions. Okay, so that in a nutshell is L'Hopital's rule. You're going to, if you get an indeterminate form, you're going to take the derivative of the top and the derivative of the bottom. Now I should say this is a simplified version of L'Hopital's rule. We've talked about one indeterminate form. Let me give you a few of the other ones. There's actually like 8 different indeterminate forms. There's 0 over 0. There's infinity over infinity. There's infinity times 0. There's infinity minus infinity. There's 1 to the infinity, 0 to the 0, and infinity to the 0. So this is a huge list of indeterminate forms, and all of them are handled using L'Hopital's rule, but you have to do a little bit of work before you can start using L'Hopital's rule on them. We have only talked about this 0 over 0 one. That's the only one that will be on your AP test. So that's the only one we're really going to work on. But do know that when you get to college level calculus, you will do all of these. So when you take your first semester of calculus in college, if you have to do that, then you'll talk about all the indeterminate forms. But if you're really good at using 0 over 0, that would be a great foundation to lay the rest of them on. Okay, go ahead and jump to your homework now. Because we've only done one of the 8 indeterminate forms, your homework is not very long. It's only about 10 problems, I think. I'll post an answer key as well. When you're finished, though, with this homework, I want you to read the first half of 8.3. I know most of you guys aren't reading the textbook before every class, but 8.3 is a doozy, and I want you guys to have some frame of reference for it before we get to class. So read the first half of 8.3. Next class, we're just going to do the first half of it. So that's pages 403 to 405. You can stop when it starts talking about cylindrical shells. And that'll just help us to kind of get a head start on what we're doing next time.